So today we have Elaine Shi from CMU who's going to be telling us about Oblivious RAM.
Okay, yeah, thank you so much for inviting me. I'll tell you how Oblivious RAM evolved from on-paper theory to large-scale real-world deployment. I think some of you might have heard of ORAM, but maybe not everyone has looked into the details of these algorithms. And today I'll also tell you how to construct an ORAM algorithm. So let me begin with the signals story, and then we can learn how to construct ORAM together. And at the end of the talk, I will mention some other applications, potentially applications that are of interest to cloud providers like Google. And I'll end with some additional challenges that lie in the way of more ubiquitous deployment. Okay. So let's look at Signal's use case first. Signal is a private messenger app, and they let you send encrypted messages to your friends. So some of you may actually use Signal, right? So they want to provide a contact discovery service. And on the cloud provider, there's a database of the Signal users. So for instance, when Andres signs up for Signal, it will ask for Andres's address book. And then it can recommend it can tell Andres, here are your friends who are also using Signal. You can connect with them. But maybe Andres is worried that his address book may be top secret. He doesn't want to disclose it. So how can we solve this problem without leaking Andres's secret? Okay, so the naive solution is we can use trusted hardware and encryption, right? So on Signal servers, they use Intel SGX servers. So trusted hardware, essentially, abstractly, let's think of it as a hardware sandbox. So inside this hardware sandbox, there's a decryption key, and all the data, when it's stored on disk or transmitted on the network, all the data is encrypted, and it's only decrypted inside this enclave, and then the enclave can perform computation, for instance, searching for your friends. So the point is, in this case, because all data is encrypted, presumably Signal cannot see the contents of the query. But it turns out that it's well known that encryption alone is not enough to ensure privacy. In particular, for Signal's use case, actually, access patterns to memory basically leak everything. For instance, if you learn which records are fetched during the search, you can learn exactly who Andres's friends are. Okay. And I also want to quickly mention that some simple solutions to the problem, they don't really solve the problem. For instance, a simple idea you may have is we can randomly permute the records as they are stored in disk or memory. And in this case, every time you fetch an entry, it may seem like you are going to a random location, but this doesn't actually solve the problem because it still leaks the anonymized social network structure. And once you learn the social network structure, it's very easy to de-anonymize it if you have some other social graph with known identities. So for instance, back 10 years ago, I had some work that shows how to de-anonymize these social network graphs. And there's also some very nice works by Arvind Narayanan and others. Okay. So I want to mention that this access pattern leakage problem is actually a quite general problem. It's not only relevant to Signal's use case. For instance, imagine you store genomic data on the cloud, and let's say the doctor is reading certain snippets in the genomic data, right? For instance, you are being screened for certain diseases. Then which snippets you look at will reveal sensitive medical information, like which disease you are being checked for. So this is one example. And we can also think about it from a programming language perspective, right? So think of a very simple binary search program. The actual code here is not too important. But in binary search, we first look at the middle element, and depending on the result of the comparison, we either recurse on the left half or the right half. So if you learn the sequence of memory accesses, you can learn exactly how large is the search key. So here, it's another example where access patterns leak everything, even if the data is actually encrypted. So more generally, if you have a program and the program conditions on some secret variable, like let's say the last bit of the secret key, and then depending on the result of this condition, you either read memory location X or Y. So in this case, if you learn which memory location is accessed, you can also learn the value of the secret variable. And there are many works that show, the extent of damage, like for access pattern attacks. So here's just one of them. For instance, this is a group of researchers from Microsoft Research and UT Austin, and they ran some off-the-shelf image processing software inside an SGX enclave, and they only observed coarse-grained access patterns. They only observed the page-level access patterns, and they show just by such coarse-grained access patterns, they can recover the location and shape of the objects. Okay. So therefore, the interesting question we want to answer is, can we probably defeat such access pattern leakage? But of course, we want to do so in a way that preserves the efficiency of the program. So back to Signal story, and they started working on private contact discovery. I would say like seven or 8 years ago, and back then they came up with a naive solution. So the most naive solution is like every time you receive a query, you can linearly scan through the whole database. In this case, of course, the access patterns don't leak anything. But the problem that it's hugely expensive because for every query, you have to linearly scan through the database. So they do something slightly more cleverly, like they take a batch of requests and they serve a batch in a single linear scan. Nonetheless, it's still very expensive because their user database has billions of users. So the overhead of this approach is like n over beta, where n is the number of users and beta is the batch size. So with batch linear scan, they used to have 500 servers to be able to serve all their workload. And eventually, around a couple of years ago, they realized, oh, actually, we should just use an ORAM algorithm because like these are actually really simple algorithms that are kind of like a binary tree-based data structure. Like I'll tell you how the algorithm works later in the talk. Specifically, they deployed a scheme called Path ORAM, which is like a paper we worked on back in 2013. And this gets you log squared overhead in theory. So I want to mention in practice, so there are two logs, right? One of the log has a very large base. So in practice, it actually behaves like log n because one of the log n is kind of just like 2 in practice. And then they were able to reduce from 500 servers to 6 servers. So this saved them like 100x in server costs. Okay, so this is a Signal story. And naturally, now you are curious how this Path ORAM algorithm works. And let me tell you what is ORAM and how Path ORAM works. Okay, so first, what is ORAM? It was first proposed by Goldrick and Ostrovsky back in the 1980s. And it's an algorithmic technique that probably obfuscates the access patterns. So the security that ORAM offers is very strong. Like basically, you can get security as strong as encryption. It's as if the access patterns are also encrypted. But of course, behind the scene, it's not really encrypting access pattern because access patterns are kind of like a side effect of program execution, right? So it doesn't make sense to say, oh, we encrypted. What really happens is like behind the scene, you permute the data in memory, but you keep moving things around as the program executes. And we can do it in a actually provably secure manner, as I will explain later. From an abstraction level, the input to ORAM is logical addresses you want to read or write, and it will translate every logical memory request into a sequence of physical accesses. So one logical request may be translated into multiple physical accesses, and the ratio of the physical accesses over the logical request, so that ratio is essentially the multiplicative overhead incurred by ORAM. And the security it provides is that essentially, regardless of your logical request, the distribution of the physical accesses should be indistinguishable. Okay, so yeah, I just want to quickly mention, like sometimes I refer to the addresses like on the left-hand side as logical addresses just to differentiate from physical accesses. And if we were to implement ORAM for hardware enclave, like for instance, like Intel SGX, ORAM would be part of the trusted computing base. It would be running inside the enclave. And anything outside the enclave, of course, you can assume is controlled by the adversary. So adversary can observe memory access patterns, for instance. Okay, so I started working on ORAM back in 2011. And let me tell you the state of the art back then, and then what we have done since then, right? So back then, I started to learn about the ORAM problem. And the first paper, as I said, was published by Goldrick Ostrovsky. And they showed a very non-trivial theoretical result. They showed you can get ORAM with log cubed overhead. And this is a big improvement from this linear naive scheme, right? But the problem is that their scheme is very complex and it has astronomical constants. So it's basically just useful in theory, but it has very little practical relevance. On the other hand, Goldrick and Ostrovsky also prove a very interesting lower bound. They show that if you want to have a generic technique that takes any program and compiles it into an oblivious format, then you have to incur at least log n overhead. Okay, so given this landscape, oh, by the way, I also want to mention, when I started working on ORAM, there were also already a line of work that tried to improve the practical performance of Goldrick and Ostrovsky's original scheme, but all of them, they just follow the same paradigm as Goldrick Ostrovsky, so they kind of inherit the same drawbacks. Like even though they were able to get rid of one log n, the schemes are still complex and with large constants. Okay, so the questions I was interested in back then, there are two big questions. Like one is, can we take this, on paper theory, can we like make it practical? And the second question is like, there's an obvious gap between the lower bound and the upper bound. So can we bridge this theoretical gap? I guess in the next 10 years, we were able to like answer both questions affirmatively. Like we have made ORAM truly practical and the algorithms are actually really, really simple. And we also showed that you can construct an optimal ORAM with log n overhead. So in today's talk, I want to focus on the practical aspect. It turns out the scheme of choice in practice may not exactly be the same as the asymptotically optimal scheme. So I'll focus on the practical construction. Okay, so now let's see how to construct an ORAM. Oh, by the way, if you have any questions, you can feel free to unmute yourself and ask. Okay, so let's construct an ORAM together. And again, right, as I mentioned, the most naive idea is let's just permute all the memory blocks at random. So this does give us something, because every time we want to access a block, we'll just go to a random location. But the problem with this approach is that, so let's say I want to access logical address 9, but then I make an access to the same logical block. And then you can see like the frequency of the accesses, right? Because the two accesses will go to the same location if these blocks are not moved around. So essentially, if you just permute the blocks, what you get is one-time security. Like the scheme is secure if you promise you will access every block only once.
But so what if I first access 9 and randomly swap 9 with a random element? Sorry, just some random question. So what if I access 9 and then random swap 9 with any other random location?
Yeah, this is a very good thought, because the scheme I'm going to tell you uses exactly this kind of intuition. And the key, I can tell you ahead of time, like the key intuition is when I swap with another element, I cannot disclose which location I have swapped with, because otherwise you can still keep track, okay, where you have swapped things with, right? Okay, so you'll see how we do the swapping exactly to make it secure. So basically the idea here is like, if you don't move things around as, I guess, like I see,
yes.
As after, you want to keep moving things around. If you don't move things around, it will leak statistical information like frequency and occurrence and co-occurrence. And it is for a similar reason why deterministic encryption is not secure. So here, it also leaks statistical information. Okay, so let's keep this intuition in mind, like the one that Da observed, and it'll come up again when I talk about the scheme. Okay, so as I said, ORAM is a binary tree-based data structure. So by the way, the framework I'm going to talk about is not the original framework of Goldrick Ostrovsky. That it is a new framework for constructing ORAM that we came up with, and I think the main advantage is like this approach significantly simplifies the construction of ORAM. So okay, so imagine we have a binary tree, and every node in the tree is called a bucket. And a bucket has finite capacity. And every bucket, has like a fixed number of slots, and every slot will store either a real block or a filler block. So the real block encodes actual data, but the filler block is just like, an encryption of 0. Like it doesn't encode any information. It's only there for security. So I want to mention, I'm going to assume all the blocks are encrypted. As I fetch things from memory or disk, and when I read it, I will always re-encrypt it and write it back. So this re-encryption also hides whether I have updated the block or not. Like if I don't want to update it, I just re-encrypt it and write it back. If I want to update it, I will re-encrypt the new content and write it back. Okay, so basically the only thing the adversary can observe is the access patterns if you assume everything is always encrypted. Okay. And the most important invariant of the scheme is that every block is mapped to a random path from the root to some randomly selected leaf. So in this example, the logical block X is mapped to the blue path. And for the time being, I'm going to cheat a little bit. I'm going to assume the CPU or the enclave can store a position map. And this position map will record where every block is, like the path assigned to every block. So you may complain that this position map is very large because it is, kind of linear in size. But I'm going to tell you, just don't worry about it for now, because later on we will completely get rid of the position map. Okay. So if we do have this position map, then reading a block is very simple. Like if I want to read the block X, what do? I will just look up my position map, find out where X is, and then I will visit this blue path, right? So it tells me, okay, X is on the blue path. So if I read every block on the blue path, I'm guaranteed to find the block X. So once I find X, now let's go back to the intuition that observed, right? So at this point, I want to remove X from the current location and relocate it somewhere else. And this is very, very important, because if I don't do that, then it will leak statistical information, as I explained. So, okay, so let's relocate the block. And now the question is, okay, how do I relocate the block? And the most natural idea is I will pick a new path and assign this block to a new path. So let's say I pick a random new path, and it happens to be the green path. So I want to move X to the green path. So first, I update my position map to reflect that X has been relocated to the green path. But I also have to write the block to the green path somewhere on the green path. But now there's a dilemma. Like, so first, okay, the question is, where on the new path should we write the block X? Like, for instance, can we write it directly to the leaf?
No, I think you had be just random, right? Random over all the blocks. The randomness should be over all the blocks. I'm not sure, actually.
The answer is correct. You should not write it to the leaf. And it's what I had said earlier. Like, you want to write it to the new path, but you cannot disclose where the new path is. So if you write to the leaf, you immediately, like, the adversary can learn which new path you have moved it, right? So the next time, if your next request is for the same block, it'll go back to the green path, and the adversary can still observe a linkability. So for this reason, you don't want to write it directly to the leaf, because it discloses the choice of the new path. And for a similar reason, you don't want to write it to any of the internal nodes, because all of these nodes still disclose partial information about this new path. And so the only safe place left is to just write it to the root. And the root is on every path, right? So you basically have written it to the new path without disclosing the choice of the new path. Okay, so at this moment, I mean, obviously you are going to complain because we cannot keep adding things to the root. The root will soon overflow. But let's set this aside. And at this moment, it's very good to think about the security of the scheme, because essentially what we are doing is like every time we access an item, we write it to a new path randomly chosen, and we don't disclose the choice of the new path. So if that's the case, if you think about it, every time I access a block, it'll just go to a random path, right? And the choice of the path has not been disclosed before. So for this reason, the scheme is secure. But of course, I have to address the issue that you cannot keep adding things to the root, because otherwise it will overflow very quickly. Okay. So this is the problem I'm going to tell you how to solve, right? So the problem is that we don't want the root to overflow. So in fact, there are a few remaining problems we have to address. One is this overflow problem. And the other is we have to get rid of the position map, as I said. Like right now, we are assuming that the CPU can store like the entire position map, which is not realistic. And then I'll tell you some further improvements. Okay, so how do we resolve this overflow problem? The idea is we are going to introduce a background eviction process. And the goal of the eviction is to move these blocks towards the leaves to make sure every bucket will not overflow with all but negligible probability. And we can just do this like as a maintenance process in the background, and the cost of the eviction can be amortized to each request. There are some challenges when we design the eviction process. So at a very, very high level, we don't want to spend too much work doing the eviction, because if it's too much work when amortized to each request, the cost will be too high. But we also don't want to do too little work, because if we do too little work, then it's not enough to prevent overflow. Okay, so we have to strike a balance between these two goals. So here's one scheme that is known to work. And this was actually the scheme in the original binary tree ORAM paper that proposed this entire new framework for constructing ORAM. So the idea is every time we make a request, we will pick 2 random buckets at every level for eviction. So let me tell you what this means. So let's say, suppose in this level, we pick 2 random buckets, right? So suppose this green bucket is one of the buckets we happen to choose. And now we want to evict a block from this green bucket. And so what we are going to do is we scan through the green bucket, we find the real block, remove it from the green bucket, and we write it to one of the children. So there is only one correct child you can write it to, because the block is assigned to some designated path, right? So suppose the block I want to evict wants to go right. And in this case, you have to make a fake eviction on the left-hand side, because you don't want to disclose which side the evicted block is going to. So in fact, every time you do eviction, like let's say I want to evict from the green bucket, I'm just going to read the green bucket and then like read and write the 2 children in a fixed order. So basically, in this way, the eviction process itself doesn't disclose any information about the request, because it's just with every request, I'm going to pick 2 random buckets from every level, and then I read and write this random bucket and the 2 children. Okay. So for a similar reason, like let's say I happen to pick a bucket for eviction, but the bucket is completely empty. It doesn't have any real block in it. I still have to make 2 fake eviction on both sides for security. Okay, so this is the idea. I mean, it's easy to observe that the eviction process itself doesn't leak any information, right? Because the choice of the buckets you read during the eviction process is independent of the request. Okay, so using this idea, here's what we can prove. So suppose you set the bucket size to be log n. And using either queuing theory or measure concentration bounds, we can prove that with extremely high probability, none of the buckets will ever overflow. The proof, I don't have time to go into the proof, but at a very, very high level, like slightly imprecisely speaking, the point is like if you think of each bucket as a queue, the dequeue rate is twice as fast as the enqueue rate, because, and this is related to the constant 2 I choose. I remember I said at every level we are going to choose 2 buckets for eviction. So because of that 2, we can make the dequeue rate twice as fast as the enqueue rate, and then the queue length, the probability that the queue length exceeds R will be exponentially small in R. Okay. So at this moment, we can think about the cost of the scheme. So essentially, because every bucket is log n in size and every request will touch one path, in total, we have log square cost at this moment. But there's still one last thing I have to get rid of, which is the position map. And this is very easy because the solution can be summarized in one word. We're just going to use recursion. So remember the position map, even though it is linear in size, the size of the position map is a constant factor smaller, at least a constant factor smaller than the original data size. So we are just going to start the position map in a smaller ORAM, and then you get a smaller position map of a position map, and then you keep recursing until the position map is constant in size, and then you can just start the position map in the CPU register. Okay, so this recursion incurs a logarithmic overhead. Like if every time you can reduce the ORAM size by a constant factor, after log n steps, you'll get a constant size position map. So with this scheme, including the overhead of the recursion, the total cost will be log cubed, right? So one log n comes from the bucket size, one log n comes from reading a path, and another log n comes from the recursion. So this is not the Path ORAM scheme yet. As I said, with Path ORAM, you can get rid of one log. And which log can we get rid of? It's the bucket size log. And the key observation is that with this original scheme I described, it's a little bit silly in some sense because every time I choose a bucket for eviction, I only evict one block. But in fact, if I'm reading this block and I'm reading this bucket and two of the children anyway, I should evict as much as possible. So this is the idea. Like we are going to do the eviction more aggressively. And Path ORAM essentially performs eviction on the read path. Like so every time I have to read a block, I will grab a path, but then I will pack blocks on the path as close to the leaf as possible without violating the path invariance. So it's kind of like the most aggressive eviction algorithm on the path. And if you do that, we can show, you can just improve the bucket size to constant, and therefore the log cubed becomes log squared. And again, in the two logs, right, the log squared, one of the log, the recursion log has a very large base in practice, and the recursion log is usually just like 2 in practice. So in practice, it behaves like log n, but asymptotically, it's log squared. This algorithm is very simple, and this is like the pseudocode, only 16 lines, and I'm even counting lines such as endif and end4. It's so simple you can print it on a T-shirt. Actually, for instance, like in my undergrad algorithms course, right, like we teach like balanced binary search trees. Actually, this tree is simpler to teach than balanced binary search tree because it doesn't even have any fancy like rotation operations. It's a simple tree-based data structure. Okay, so let me summarize how to construct ORAM, right? So the key idea behind tree-based ORAM is every block is mapped to a random path, and every time you access it, it gets remapped to a new random path. And the key insight is we have to relocate the block to the new path without disclosing which path it is. The security proof is trivial, as I mentioned. The key challenge in proving these schemes is actually in the correctness analysis. Like we have to prove that when we design the eviction algorithm appropriately, we can guarantee that no bucket will ever overflow with all but negligible probability. So you can make the failure probability as small as, like, for instance, the failure probability of encryption. Okay. So this is how to construct ORAM. And I want to end with some applications and some additional challenges for, like, if you want to have more ubiquitous deployment of ORAM, like what are the additional challenges? So let's first talk about applications. So when I browse Twitter, like I often see these Twitter posts, oh, when do you need a blockchain? And then there's a decision tree. So I decided to do a decision tree for when you use when you need an ORAM. Okay, so when do you need an ORAM? The first question you can ask is, oh, do you need trusted hardware? if you need trusted hardware, then chances are you might need ORAM, like unless the computation task you have is not interesting. Because for anything that involves like data structures make dynamic memory accesses, and the access patterns are incredibly leaky. So chances are you need ORAM if you are using trusted hardware. And there's also something I didn't talk about at all in this talk. Actually, like cryptographic techniques like multi-party computation also rely on ORAM, and because it's for the same reason, right? Like essentially, there you are replacing the trusted hardware with like a cryptographic secure processor, and this is like, so sometimes it's often neglected because people don't talk about the step of converting the program to a circuit. Like if you don't have ORAM, like every time you want to perform binary search on the database, you have to encode the entire database in the circuit. So you have a linear size circuit, and you would be doing multi-party computation over a linear size circuit. And with ORAM, you can avoid this polynomial or linear blow up. Okay. Okay, so I want to mention some applications for cloud services and for blockchains. So a talk isn't a real talk if it doesn't mention a large language model, right? So here's the ORAM application for large language model. So in LLMs, like sometimes the data gets updated very, very frequently, and retraining the LLM can be very time consuming. So there's this idea called retrieval augmented generation. And the idea is like, it's some kind of fancy table lookup, like the client submits a query, and then you basically, with the query, you will figure out like there's a knowledge base, and you want to fetch the most relevant entry from this large knowledge base. So it's kind of like a fancy table lookup. In this case, like, you know, today everyone's becoming very, very concerned about the kind of queries they're sending to like ChatGPT. So with something like ORAM, you can, you know, support something like ChatGPT, but without revealing clients' queries. Another application is like privacy-preserving outsourced machine learning, right? So for instance, if a cloud provider provides like, you know, some kind of secure MapReduce cluster, and then, you know, clients can upload their sensitive data set and do machine learning training on top of it. You may also need something like ORAM, because there, it's not just the memory access patterns, like the access patterns also reflect in a network transmission pattern. And you can also use ORAM or Oblivious algorithm techniques to hide these data access patterns. And there's also another interesting application is like something like haveibeenpawned.com, right? So this is a website. You can send your password to the website, and it will check if your password is like contained within some leaked password data set. So today, the way you do it is you send your password in the clear to this website, which means you have to fully trust this website. And this is kind of like risky, because like, what if the website itself gets compromised? So with ORAM, you can, you know, enable such applications without having to reveal the user's password. And I think also Google has some kind of services like this too. Like when you sign up for a new account in Google, Google will also like make password suggestions to you, like, oh, whether your password is safe or not. Okay, here's also some blockchain applications. So actually, it turns out the blockchain community is getting increasingly more interested in ORAM. And here are some main applications. Like the first application is to enable privacy-preserving transactions and smart contracts. The second application I want to talk about a little bit more, the use case for companies like Flashbots. So let me actually quickly mention the third application first, which is like privacy-preserving lightweight clients, right? So like, you know, if you have a mobile device and you cannot store the entire blockchain, and so you are just basically using a light client, and whenever you want to fetch some relevant, you know, transaction from the blockchain, you will send your query to a cloud service provider. But you may want to hide your query because it may reveal like which token you are interested in transacting. And so there's actually a company called MobileCoin, and they're providing the service using an ORAM algorithm. So I want to talk more about this Flashbot use case, because this actually, I think, is more relevant to, it's like similar to what a traditional cloud provider is interested in. So what is Flashbots? Like Flashbots is, they're like a central player in layer one. So layer one is the consensus layer for blockchains. And it turns out basically, even though blockchain was like designed to be a decentralized environment, like it turns out the ecosystem is becoming kind of centralized. So with blockchains, like you have these, it's called like automated market makers. Like these are contracts where you can trade, for instance, Bitcoin with Ether, or trade like multiple crypto assets. So imagine there's some victim user who submits a transaction to like a public pool. And let's say, this user wants to buy Ethereum at the price of 6. And the current price is like 3. So what a searcher does is it discovers this price difference. So it will insert a transaction before the victim's transaction and insert another transaction after. It will say, okay, I'm going to buy before you, which will raise the price to 6, and then I will force you to buy at 6. And after your transaction, I'm going to immediately sell what I have bought at a higher price. So this is kind of like risk-free arbitrage opportunity, like through this back-running and front-running and back-running. Okay, so what Flashbots offers is like for these searchers or arbitragers, it promises to confirm this bundle as an atomic bundle, so that you're guaranteed to make risk-free profit. But then also interestingly, Flashbots sell exactly the same service to users. Like basically, it's offering favorable positions in the block to both the users and to the arbitragers. And to the users, they promise, oh, if you submit your transaction through us, we guarantee you will not be front run and back run. So it's a little bit paradoxical, but that's their business model. So essentially, they're like a block builder, right? And they're very concerned about earning their customers' trust because they're in the perfect position to front run and back run everyone's transactions. So they want to make sure, that their customers trust that they're not doing these things. So they're looking into a solution based on Intel SGX, and there they will also need to rely on ORAM because, like inside the SGX enclave, they will have to speculatively execute like the EVM virtual machine, and the access patterns there are very, very leaky. Like it can leak things like, oh, which crypto asset you are trading, like who is the sender, who is the recipient. So basically, they're starting to like look into SGX and ORAM based solutions. Okay. So finally, I want to conclude by mentioning some of our ongoing efforts and what kind of challenges we are trying to address with these ongoing efforts. So right now we are trying to build an Oblivious STL library. It will be an open source library. Like you can think of it as Oblivious counterpart of the standard C++ STL library. Like so essentially for common data structures like map, set, priority queue, range query, for common algorithms like sorting, shuffling, graph algorithms, we want to offer Oblivious counterparts for all of these algorithms. So let me quickly mention, like there are 2 ways to deploy ORAM. Like one is a completely legacy compatible way. Like for any algorithm, like let's say you have your current program which you want to run in the enclave, you can take ORAM and generically compile it into an Oblivious counterpart. So this is already quite efficient because you can see that the Path ORAM algorithm is very simple. But if you are willing to like take your program and replace each of the building block with a more customized Oblivious counterpart, you can potentially get better performance. Like there's often like a logarithmic factor you can improve by doing this customized approach. And this is one reason why we are building this Oblivious STL library. Okay, so some of the challenges for more ubiquitous deployment. I guess one challenge is just lack of awareness. Like a lot of the current blockchain projects, like there are many blockchain projects, for instance, that use trusted hardware to get privacy-preserving transactions and smart contracts. And they don't use ORAM yet, and I guess partly because of lack of awareness. Like, and for this reason, they don't actually offer the promised security, because if you can observe the traces of the EVM execution, it leaks like who's the sender, who's the recipient, which crypto token you're trading, and there's been like some security analysis of these blockchains. And also another example, I guess, is just like Signal. Like Signal, they wanted to have private contact discovery, but it took them like 5 or 6 years to realize, oh, you know, this is the right algorithm we should have used. So actually, it's very interesting to contrast ORAM with zero-knowledge proof. Like in the blockchain community, zero-knowledge proof has much more awareness. Like, I mean, partly because like zero-knowledge proof can enable these scaling applications. But actually, if you compare ORAM and ZKP, like ZKP is much more complicated, mathematically speaking. And for zero-knowledge proof, there are many, many different schemes, and there's no one-size-fits-all solution. Whereas for ORAM, the landscape is very different. It's like these algorithms are extremely simple, and for everything, almost everything you want to do, there is a one-size-fits-all solution because like the upper bound and the lower bound are just tied up to small constant factors, and there's very, very little room for improvement for these algorithms. So another challenge is what I said, that there's this generic but legacy compatible way of taking your existing program and just compiling it to an Oblivious counterpart using generic ORAM. But you can get more performance if you have customized algorithms for each computation task you care about. Like we can have Oblivious data structures, sorting, shuffling, graph algorithms, and this is one strong motivation to have the Oblivious STL library. A third challenge is like sometimes there's a mismatch of the performance metric, like because let me explain, like most of these algorithm papers, they are written assuming a simple word RAM model. And the point is like in the algorithm literature, we don't differentiate between the computation overhead and the memory access overhead. But if you are going to deploy ORAM for like architectures like Intel SGX, then you have to make this differentiation because there a significant overhead comes from page swap. Like because every time you want to read something that's like an encrypted memory location on disk, you have to swap in an entire memory page to read that location. You cannot just like, it doesn't make sense to swap in a single byte because the page swap comes with its like own overhead. So this actually, so yeah, as I mentioned, like the challenge is because the enclave often needs to fetch encrypted data from external memory or disk. And the page swap is a heavyweight operation because it involves like system call, encryption, decryption, and it also involves possible disk swap. So if you just implement ORAM naively, what's going to happen is that the page swap cost will be very, very dominant. Like for instance, in an earlier work by a group at Berkeley called Oblivious, in their implementation, you can observe that the computation overhead is less than 10%, but the page swap overhead is dominant. And then we basically redid their effort. Like so Oblivious provides Oblivious map data structure. So we basically improve the algorithm using these techniques from the external memory algorithm literature. And there we can achieve an asymptotical improvement in the number of page swaps. So with our implementation, the page swap overhead and the computation overhead are roughly equal. And in comparison with Oblivious, we have like orders of magnitude improvement in performance. This is actually somewhat surprising because like if you think about it, ORAM is such a simple binary data structure. But when you actually implement it for a practical architecture, there are still additional algorithmic tricks you can do to like, because of this performance mismatch issue. Okay, finally, another challenge is like the security of the Oblivious implementation itself. And this is also interesting because like, for instance, when we look at the code of Oblivious, which is the same prior work I mentioned, actually, the code is not, it doesn't offer the security they promise in the paper. In particular, they have conditional branches that branch on some secret variable. And inside these two branches, the memory access patterns are not the same. So, but it turns out that this problem, like from an academic perspective, it's also a solved problem because earlier we have proposed these memory trace Oblivious type systems. So essentially we defer the problem to the compiler. Like the compiler, when it compiles the program, it can check for you whether your program is secure or not. So you don't have to rely on the wisdom of the developer to guarantee the security of their implementation. Okay, so basically these are the things we want to be able to like achieve with this Oblivious STL library. And besides what I mentioned, like we also want to have like parallel implementations of these algorithms. And we also want to, for instance, incorporate these type system and compiler techniques to be able to guarantee the security, mechanically rather than having to rely on a human. Okay, we have some preliminary open source. In particular, the enclave-based implementation is at the first URL, and the second URL is just like some reference algorithmic implementation. So far we only have an Oblivious map and Oblivious sorting and shuffling. Obviously, there's like a lot more we want to do. Like we want to offer, all of these other data structures and common algorithms. Okay, so to conclude, I discovered that when you go to coffee shops in Pittsburgh, there's this donut you can buy. It's called ORAM. So do you need an ORAM? Yes, because it's delicious. And if you ever come to Pittsburgh, I will buy you an ORAM. Thank you.